Continuing our study of parametric curves, we're going to take a look at symmetry and concavity for parametric curves. And to do that, rather than doing something formal and general, we're just going to introduce this on an example. So let's say we want to sketch the parametric curve of equations x of theta is 4 cosine cube of theta and y of theta is 4 sine cube of theta. So because x and y are both defined in terms of cosine and sine of an angle, and these two functions are 2 pi periodic, then certainly so are x and y. And therefore, we can restrict ourselves to the angle theta being in an interval of length 2 pi if we want to trace out the curve once. So we can restrict theta, for instance, to the interval negative pi to pi. A second observation is that if we plug the opposite of the angle theta inside x and y, then you see that because the cosine of an angle is the same as the cosine of the opposite of the angle, then x is the same, whereas the sine of an angle is the opposite of sine of negative that angle, and therefore y of negative theta is negative y of theta. And what that means is that when we have a point of coordinate x of theta, y of theta on the curve, then the corresponding point of parameter negative theta is in fact the symmetric of that point with respect to the x-axis, because it has the same x value but opposite y value. So we have a symmetry with respect to the x-axis, and therefore we only need half of the interval negative pi to pi, and we get the other half using that symmetry. Similarly, if I replace the angle theta by pi minus theta, then that changes the cosine into its opposite and the sine is unchanged. Therefore, when I replace theta by pi minus theta, I get an opposite x value and the same y value, which represents a symmetry with respect to the y-axis. And because we have this symmetry, we don't need to study the curve on the entire interval 0 pi, but only on half of it, on the interval 0 pi over 2, and we get the other half using that symmetry. So we can restrict ourselves to theta in the interval 0 to pi over 2, and we'll get just a piece of the curve, and then we'll draw out the rest of the curve by using the fact that we have two symmetries, one with respect to the x-axis and one with respect to the y-axis. So on that interval, to study the curve, we're going to look at the derivatives, intervals of increase and decrease of both functions x and y. If we differentiate the function x with respect to theta, when we differentiate cosine cube of theta, we use the chain rule and we get 3 cosine square of theta multiplied by the derivative of cosine theta, which is negative sine theta. Therefore, the derivative is here negative 12 cosine square theta multiplied by sine of theta, which is of course a non-positive value. Similarly, the derivative of y is obtained by multiplying 4 by the derivative of sine cube of theta, which we obtain with the chain rule, and is 3 sine square of theta multiplied by derivative of sine theta, which is cosine theta. Therefore, we get 12 sine square theta cosine theta, and that's a non-negative number. So we have this situation. If we look at theta restricted to the interval 0 pi over 2, then what we have is that x prime and y prime both take the value 0 at 0 and at pi over 2, and x prime is negative on the rest of the interval and y prime is positive on the rest of the interval. What that means for x and y is that x is decreasing from 0 to pi over 2 and y increasing from 0 to pi over 2. The value of x at 0, if you plug theta equals 0 in the expression for x, you get 4 times 1, so x is 4, and at pi over 2 the cosine is 0 and therefore x is 0, whereas for y, when we plug 0 we obtain 0, and when we plug pi over 2 we obtain 4 times 1, so 4. So x is decreasing from 4 to 0 while y is increasing from 0 to 4. We might want to ask about the slope of the tangent at particular point, and in particular at this special point where the parameter takes a value 0 at pi or pi over 2. As we have seen, to get the slope of the tangent line for a particular value of the parameter, we look at y prime divided by x prime, and we found y prime and x prime. So we get this 12 sine square theta times cosine theta divided by negative 12 cosine square theta sine theta, and when we cancel things out we obtain negative tangent of theta. In particular, that means that when the value of the parameter is 0, then we obtain 0. In other words, we have an horizontal tangent at the point of parameter 0, which corresponds to x equals 4 and y equals 0. On the other hand, when the parameter approaches pi over 2, then the tangent is approaching infinity, and therefore we have a vertical tangent at the point of parameter pi over 2, where x is 0 and y is 4. So in other words, if we start trying to draw out the curve, if we look at the point of parameter 0, x takes a value 4, y takes a value 0, and we have an horizontal tangent. So we have something like that. If we look at the point of parameter pi over 2, x is 0, y is 4, and we have a vertical tangent. So we have something like that. And now to draw the curve, knowing that x is decreasing from 4 to 0 and y increasing from 0 to 4, it would be good to know something about the concavity of the curve. And just like in the case of the graph of a function, this is determined by the sign of the second derivative of y with respect to x. Of course, here the derivative of y with respect to x should be thought of as a local rate of change of y with respect to x, iterated rate of change. So in this case, we can think of that as a rate of change with respect to x of dy over dx, which as a function of theta we have found to be negative tangent of theta. We can use the chain rule here to say, well, the rate of change with respect to x is like the rate of change with respect to theta multiplied by the rate of change of theta with respect to x. And so we get the derivative with respect to theta of negative tangent of theta. Then we multiply by the rate of change of theta with respect to x, which is really the reciprocal of the rate of change of x with respect to theta, in other words, x prime. That means we get the derivative of negative tangent, which is negative secant squared of theta, and we divide by what we have found to be x prime. In any case, we get something positive, because we are restricted to the interval 0 pi over 2, so cosine and sine are both positive, at least on the open interval. And so we have something negative over something negative, we get something positive. A positive second derivative here, this d2y over dx2, means that the curve is concave up on the open interval from 0 to pi over 2. And therefore, with x decreasing, y increasing, and the concavity is up, we should expect a curve that looks like that. So that's the part of the curve corresponding to the interval 0 pi over 2 for the parameter. But now we know that we have a symmetry with respect to the y-axis, which gives us this other part of the curve, and a symmetry with respect to the x-axis, which completes the curve now. So now we have completed our sketch of this parametric curve. Now turn to the next video, in which we're going to discuss how to find the area enclosed by a parametric curve.